If you're watching this video, chances are you've taken a picture with a modern camera before. You also probably carry around that camera in your pocket every day because it comes pre-packaged in your smartphone. Take a look through your camera roll and stop to appreciate how clear those photos and videos look. You might be wondering how such a tiny device can create and store lifelike images in a matter of seconds. The answer to that question is just one word: semiconductors. Like the name suggests, semiconductors are materials that have a conductivity between insulators, which can't conduct electricity very well, and conductors, which conduct electricity very well. Some common uses for them include silicon transistors used in phone and computer chips, LEDs, and of course, camera sensors. What makes them really special, however, is that their conductivity can change when exposed to a certain stimulus, like light, heat, or electricity, which makes them ideal for controlling circuits. Inside your phone camera, for example, there's an array of diodes that are able to absorb light, generating small currents that can be converted into image data. These sensors are great for picture taking because the diodes in the sensor are great at detecting light in the visible spectrum. While light detection for visible wavelengths is cool, for some applications it would be more useful to be able to detect wavelengths that we can't see, which is what our lab focuses on. We specialize in making low-cost, high-efficiency infrared light detectors using silver selenide quantum dots, which are microscopic semiconductor nanoparticles that can be suspended in colloidal solutions, allowing quantum dot films to be deposited on substrates, like how a printer deposits ink onto paper. The current forefront of IR detectors use materials like lead sulfide and mercury cadmium telluride, which use highly toxic metals. Furthermore, some of these materials need to be cooled down using liquid nitrogen to function properly. Their toxicity and need for cooling reduce these materials' accessibility and increase operating costs significantly. On the other hand, silver selenide detectors can operate at room temperature and do not use heavy metals, making them relatively cheap and environmentally friendly. With more accessible and accurate IR detectors, technologies for monitoring crops, cancer imaging, thermal imaging, and more will also become much easier to access. The process starts with the quantum dots themselves, which are synthesized in lab. We use the hot injection method, which involves injecting a precursor solution of one metal into a heated flask with another precursor in it. For silver selenide, a selenium precursor is injected into a heated silver precursor at 170 degrees Celsius. This method allows for a synthesis that produces uniformly sized quantum dots, which is important for ensuring effective light detection. The synthesis also coats the dots in long-chain ligands that allow them to stabilize while in solution. These ligands are good for ensuring that the dots are stable during synthesis, but they do interfere with electrical conductivity because of their size. The distance between dots is quite large with these ligands, so forming a good film with the dots as synthesized is difficult. To fix this, we use the solution phase ligand exchange to replace the long ligands with shorter ones. It starts with two distinct solutions, a nonpolar phase with the dots and a polar phase with the ligands we want on the dots. These two solutions don't mix at all initially, but when the mixture is agitated, they are forced to interact, causing the long ligands to detach and fall into the nonpolar phase and the shorter ones to replace them. The exchange is evident when the dots transfer from the nonpolar phase on top to the polar phase on the bottom. After the ligands have exchanged, the solution is cleaned with nonpolar solvent to remove excess long ligands. With the exchanged dots, it is much easier to make a fast, conductive, and responsive film. The efficacy of the device depends on a multitude of factors. We are currently trying to optimize our devices to be fast, long-lasting, and have a strong response to light. To this end, we've experimented with different ligands, film depositions, and putting additives in the quantum dot solution. Adding polymers to the solution will impact the film's behavior as the polymers interact with the quantum dot network, impacting conductivity and responsivity. It turns out that the film can become more conductive or more stable depending on what kind of polymer is added, allowing for extra tunability for how the device is expected to function. Overall, the world of quantum dot photodetectors is a technology filled with the potential to impact many industries and fields with low-cost entry to IR detection. One day, maybe your handheld camera